Hello everyone! In this video, I will explain you how to perform contour detection in OpenCV. I will use the Python programming language. Over here, you can see the post that I created and that nicely summarizes everything that I will explain in this video. This post contains codes, contains images, and it will explain you step by step how to detect the contours. So let us go back to our original image. Over here you can see the photo that I took with my cell phone. Basically, the background is my office desk, and these are the parts that I have in my office. Now, I want to detect the contours of these items. Here are the results. So here are the contours. You can see the contour of the charger, the contours of the marker, of a paper, and I will teach you step by step how to go from here to these contours. Okay, so let us start. First, move your cursor and place it somewhere over here on the image. Then do the right click and click on Save Image As. And here I will just replace this image over here since I already have it on my disk. However, in your case, you will simply download it to a new folder and click on Save. Okay, now image is saved. And I can open my Python script that I wrote and that I will explain in this video. You can notice over here that I'm using the Spider programming environment. I like this programming environment since it reminds me of MATLAB, and if you want to execute certain code lines, you will simply select them, do the right click and run cell, and they will be executed. Now, make sure over here that basically the path is in the folder that you have already created and that contains the image file. That is, the path should be adjusted such that the current folder is the folder in which your image is saved. Now, let us import the libraries. This library is the OpenCV. Then I will import plotting tools and I will import NumPy. So let's do that. Now, in my previous video, I explained how to display images, and I will quickly go over this piece of code. So, to display these images, you will simply select the code lines, these code lines. You will enter here the name of the image with the extension, and over here you will call the function cv2.imageShow. Then you will call cv2 wait key, and at the end you will call destroy all windows. So let's execute this. Okay, so here is my image. It's too large, right? It's too large. So the first thing what I need to do is to resize this image. So to close this image, you can press any key, right? Any key will basically destroy the window. If these steps are not familiar, that is, if you don't know how to display image, my advice is to read the post that I created and to watch the video. A link is given in the description below. Okay, so let us resize the image. Here I select the scaling factor. I will choose 60%. And here I will calculate new width, new heights, and I will calculate new dimensions. Place it in a tuple. And let's see what we have right now. Okay. Now new dimensions will be 691 by 921. Okay, so let us resize the image. And here's my resized image. Okay, this is the resized image, and then I will save this image as resized parts.png on my disk. You can save the image by using this function cv2 image write. You specify the file name, you specified the source image, and here you can play with the compression levels. 0 means no compression and 9 means the maximum compression. Okay, so we need to follow several steps in order to detect the contours. The first step is to convert the image to grayscale. Okay, so why do we need to convert an image to grayscale? Well, if you look into our original image or resized image, let's see what happens here. We can see basically that the image has basically 3 dimensions. Okay, so 921 is the height, 691 is the width, and we also have, for every pixel, we have 3 channels. These channels are RGB channels. However, you should be careful because Python doesn't represent basically images as the RGB. It basically opens them as BGRs. Okay, be mindful and keep in mind these things. So there are 3 channels, so I need to basically kind of merge these 3 channels in a single channel, and the easiest way to do that is to convert the image to grayscale. So let us convert the image to grayscale. We call this function, we enter the image name, and then we basically choose the flag that basically converts to gray. So let's do that and let's see our image. Okay, here's our grayscale image, right? Now, if you now look into the shape or the structure of this image, you will basically notice that this image now has, let's see, should have 2 dimensions, right? It has only the height and the width. Okay, and here I save my image to my disk, right? Since I will need this image for some future operations. Okay, so this was the first step. That is, we have converted the image to grayscale. The next step is to threshold the grayscale image. So what is thresholding? Well, let's illustrate that through this particular example. So this function, cv2.threshold, will threshold the image. 90, the second argument, is the threshold value. 255 is the third argument, and this is basically the value that will be assigned to pixel values that are larger than 90. That is, this value will be assigned to the value stored at certain pixel that is above 290. So for example, if at the pixel 5,3 the value was 100 in the original grayscale image, it will become 255. However, if the value at certain pixel, let's say 3,7 was 70, then the value will be assigned to 0. So this is thresholding, and here I select the binary way of thresholding, meaning that I either go to 0 or to 255, and 90 is some kind of the thresholding level. That is, every value that's below 90 is assigned to 0, and every value that's above 90 is assigned to 255. So let's look into our thresholded image. Let's see what happens. Okay, so here's our thresholded image, right? The grayscale. Then we apply a threshold and we obtain a black and white image. Now, this is the first way of thresholding, where I specifically enter the value of the threshold. Okay, but there is another way of thresholding. This is the so-called Otsus method. So I will use the Otsus method for image thresholding. The nice property of this method is that this method will automatically find the optimal value of the threshold. And this function with this flag, thresh binary, then vertical bar cv.thresh_otsu will automatically determine the most optimal value of the threshold. Okay, so let's see what happens when we apply this threshold. Okay, it looks similar to the previous image, right? However, the difference is that over here we don't have these small white dots. So let us open these two images. Okay, let's actually save this image as number 2. Okay, and let's apply the code again. Now let's just comment the Otsus method and let's apply this thing and let's see the differences. Okay, so this is basically the standard thresholding, and let's compare these two images. Okay, so this is the first one, and let's open the second one. Okay, we can bring them next to each other and let's see what happens. Okay, so this is the Otsus method, right? Otsus method. And this is the standard method of thresholding. We see that this method seems to be better, right? Seems to be better. However, I will show you later that actually the most primitive method will produce best results when detecting contours, and we will see that later in the video. Now, let us close these two images. Let us go back to our code and let's stick with our standard thresholding, right? Let's apply this code again. Here's our image. Now, let us plot the histograms of thresholded and grayscale images just to convince ourselves that we are doing the right thing. Let's see what happens. So this is the grayscale image, and this is the color histogram of grayscale image, meaning that this represents the distribution of pixel values starting from 0 to 250, right? And here's the binary image, thresholded image. We see that basically the values are either 0 or 255. Okay, so this was the second step. Now we have the thresholded image. The next step is to determine contours and to filter them. Okay, so let us call this function cv2 find contours with the first argument equal to threshold image. The second argument is this flag over here, and the third argument is another flag that I will explain in the sequel. So if we execute these code lines, we have computed the contours. So we have the contours and we have the hierarchy of the contours. Now, these two parameters over here, or these two flags, have a special meaning. Now, you can read more about these parameters and these flags in my post. For example, the first argument, actually the third argument in this function, cv2 chain approximation simple, removes the unnecessary points and thus it saves memory. That is, basically, when you compute the contours, right, for example, this contour, basically this will be the whole contours, and you can save a bunch of these points, right, on the contours. However, that's not the memory efficient way. More memory efficient way is, for example, to save these 4 corner contours, and in that way you basically can save the memory space. So the argument over here, basically chain approximation simple, that is the third argument, means that you're basically optimizing the computed contours, or you're optimizing how to save them. Okay? Now, the second parameter is another important parameter, and it's being explained over here, right? So This parameter is basically used to organize hierarchy of the contours. Basically, every contour that's being computed has a certain hierarchy. Now, according to the OpenCV documentation, this flag finds all the contours and organizes them in two-level hierarchy. So you can click here and you can read over here what are the hierarchies, how they are organized, and you have several ways of organizing hierarchies. So for example, if these are the contours, this one is at the top of top level hierarchy, then this one is at the second level, etc. So you can read more about these things. However, for using this code, you don't need to basically understand in details how the hierarchy system works, since we will use just basic functionality. However, if you want to, for example, filter out certain contours or to select certain contours inside of other contours, these flags are very useful. However, since this is just an introductory video, I will not go more into these details. I will probably make a video that will explain the contours. Now, once we have computed the contours, we will make a copy of the image, of the original resized image, the color image, since I will basically plot, or I will add contours to the color image, and I don't want to ruin my original image. Now, this for loop over here will go over the contours, right? And it will calculate for every contour its area. Now, if the area of the contour is smaller than certain threshold value, we will neglect these contours, or if the area is larger than certain threshold, we will also neglect these contours and we will not draw them. So we will draw only contours whose areas are in certain limits. Okay, so let us see what will happen if I don't use this filtering. So I will just uncomment this thing, right? This code line, and I will basically draw all the contours. Notice here that nothing happens since I'm not plotting the image. This code line will just draw the contours in the original image. However, it will not display the image. So this code line will draw all the contours without filtering. I'm not executing the for loop. I'm just doing this for illustration purpose. So let us see the result. Okay, so here are the contours. I can see many contours that I actually don't need. I can see these points here. They're also contours. I can compute the contour for any point over here. I see here some contours inside. I see contours. Okay, that's why I need to perform the filtering. Okay, so I will kill this window. Again, I will recompute my resized image copy, and I will comment this line. And let us now execute the code and let's see what happens. Now I'm executing the call, the for loop, and I'm only adding the contours to my image that are between certain area range. So let's see what happens. And let us finally display our image. So here's the result. We can see nice contours over here. There are no artificial contours over here, and the results are relatively okay. Now, let us repeat this procedure. However, this time we will use the Otsus Threshold method. So I will use the Otsus Threshold method, and let's see what happens. Okay, first close this original. This is the binarized image, and let's see what happens. So notice here that this method didn't select the contours properly, or didn't compute the proper contours, because over here it somehow has problems to detect the green color, right? So the green color is probably somehow lost in the thresholding process. Okay, that will be all for today. I hope that you liked this video. If you like the videos I make, please subscribe or support my channel. Have a nice day and see you soon.